In this video for section 15.1, we're going to talk about writing linear regression equations with multiple independent variables. In section 14.2, we wrote these equations with one independent variable. So when we write an equation with multiple independent variables, each variable will have its own slope. So we will be labeling these variables with subscripts that have numbers. So x1, x2, x3, x4, etc. for however many variables we have. The slopes will be labeled accordingly, b1, b2, b3, for however many slopes we have. And there's only going to be one constant term in the equation, or the intercept, which will be b0. So this is what the multiple regression model or equation will look like. Y equals b0, the constant, plus b1 times x1 plus b2 times x2 for however many x's we have. So we're going to use Minitab to find the equation, of course. We're also going to use Minitab to test the hypotheses about whether the overall model is significant. So our null and alternative hypotheses for these tests will look like this. And this should look somewhat similar to the null and alternative hypotheses for an ANOVA test. The null hypothesis is that each slope coefficient is equal to 0, for however many slope coefficients we have. They're all equal to 0. Our alternative hypothesis is that at least one of them is not equal to 0. So note that it's not that all of them are not equal to 0. One or two of them maybe are equal to 0, but at least one of them is not. If we fail to reject the null hypothesis for this test, and we can't determine that our overall model is significant, then we really don't want to use this model for describing the situation or making predictions. As we saw in section 14.2, we can also test each slope for significance. The null and alternative hypotheses for doing this. The null hypothesis will be that that particular slope is equal to 0, and the alternative hypothesis will be that that particular slope is not equal to 0. And if we're going to use our regression model to make predictions, we should not have any insignificant variables in our model. So if we find that we cannot reject the null hypothesis for any of these slopes, then we would want to take those variables out of our model and rerun the model before we use it to make predictions. So we're going to look at example 15.1. We have a real estate firm that wants to develop a model that can be used to determine the selling price for a house. And they have this list of independent variables: home size in square feet, age of the house, number of bedrooms, number of bathrooms, and the garage size, or the number of cars that the garage can hold. So as you can imagine, all of these might be variables that affect the selling price of a house. So we have some data on 319 properties, and we want to use this data to build our model. So if we go to Minitab, this worksheet is in Blackboard. You can see that we have data on the selling price of the houses, the square feet in each house, the age of the house in years, number of bedrooms, number of bathrooms, and the garage size. So what we're going to do to build our model is go up to Stat, go down to Regression, and then go over to Regression again, and Fit Regression Model. Our responses box is where we're going to be putting what we want the y variable to be. So in this case, I want my y variable to be the price, because I want to be able to predict the price of the house from all the other variables. In the continuous predictors box, I'm going to put the rest of the variables that I want to use for my x variables. Well, in this case, it's the rest of them that are in the spreadsheet, but I guess there could be others in the spreadsheet that you don't want to use. And when you put these in, you want to put them in order, because Minitab is going to give them back to you in order. So if you just kind of randomly click on them to select them, then they're going to be all mixed up when you go to write your equation. And that's going to make it a lot harder to do the homework problems. So put them in an order and they will come out for you nicely in order. Then I click OK. And here's what we got. We have our regression equation here. So price equals, and then we have the constant term, $31,128 plus 6,307 times the number of square feet minus 1,144 times the age, etc. So square footage is x1, this is x2, x3, x4, and x5. So when I go to write that down, I'll use those variables instead of the words. As we saw before, if I want to see more digits after the decimal point for these numbers, I go to the coefficients table, click on the coefficients column, and I can adjust the decimal places here if I need to. So what I'm looking for here in terms of the testing for significance, the overall model test for significance will be in this analysis of variance table. So the F value here is 277.77 with a p-value of 0.000. So if I'm using an alpha of 0.05, I can reject the null hypothesis and say that the overall model is significant. If I look at the R squared value, or the coefficient of determination, 81.61% of the variation is explained by the variables in this model. So there are still other factors that go into play in terms of determining the price of a house, which shouldn't be too surprising. Factors such as location, there's other factors that are going to determine the price. And then for testing each individual slope coefficient, I'm going to go back up to the coefficients table. Here are the t values. So you're not going to need to put them in for the constant term, but for each of these variables listed here, we're going to identify the t value and the p value. So for the homework, you're going to need to put in t values. I'm looking at p-values to determine whether I reject or fail to reject the null hypothesis. And as you can see, if I'm using an alpha of 0.05, all of my p-values are less than alpha. So that means that I would reject the null hypothesis for all of my slope coefficients, and I can say that they all are, we have evidence that they all are not equal to 0. The biggest p-value here is 0.027. If I used a smaller alpha of 0.01, then I would not be able to reject the null hypothesis for this one. But 0.05 is going to be greater than 0.027. So for an alpha of 0.05, I would reject the null hypothesis.